Hi all, and today we are going to discuss about solid state sensors. And in last few classes, we have already discussed about some kind of sensors that is working under the principle of Hall effect. And I have already showed you a video relating with Hall effect. And now we are discussing some points on solid state sensors. And the function of solid state sensors depend on the presence of magnetic fields. Obviously, the change in the magnetic field that influence to change the electrical conduction of a conductor, in sense of a semiconductor. I am saying about. And so, if you are keeping a conducting material near to the presence of magnetic flux, and if the conductor carries current, then if is there any kind of magnetic flux changes that is occurring surroundings, then automatically that will influence the flow of current or flow of electron through that particular material. And that is the main basic principle of store solid state sensor. And obviously we can easily say that that is Hall effect sensors. And some cases it may use magnetoresistive sensors, and that is also related with solid state sensors. And some material have the property to change the resistance of that conductor or that particular material when we are keeping that material near to a magnetic field. Okay, and now we are going to discuss some detailing about these kinds of solid state sensor here. And the third point, the charge carries that flows to the semiconductor material experience a sideway action in the presence of transverse magnetic field. And normally we can call it that there is a force, and that is denoted in sense of Lorentz force. And the magnetic field of Lorentz force we can easily expressed in a normal equation that is denoted here F is equal to Q sigma into JB. And Q is nothing but the electron charges. Then conductor obviously we have some kind of charges, particle or electron will take care of the movement of the current through that conductor. So the electron charges we can represent in the form of Q, and sigma is the material conductivity, and J is the current density, and B is the magnetic field density. And if a change in the magnetic field density will influence to change the Lorentz force occurring the resultant. Okay, that we can easily analyze with this simple equation. And moving to the next slide, and this is this common setup that we can normally call it as a sensor with solid state or a solid state sensor. And we have a magnet here, and the semiconductor sticking of the magnet, and obviously we require an exciter wheel. And with the presence of this magnet and with this exciter wheel, the influence of the magnetic field or magnetic flux inside this semiconductor by this magnet will change at the presence of this exciter wheel dip and tweet and dip positions. And we can say that if the teeth position it comes near to the semiconductor material, and while moving it, and it will change the normal flex linking to that material. And obviously we have already discussed with this thing, the teeth and dip structure will influence to change the magnetic flux when we can say it in the case of normal. And moving to the next slide, solid state sensor analysis. And for any sensor, when we are considering in detail, the output of the sensor, it should be in the form of some kind of electrical signal. And obviously, we can say that all signal or sensors will give you the physical quantity into an electrical quantity. And here, the rotational movement or a linear movement that possessed with the help of your exciter wheel will give you some kind of electrical signal at the output of the sensor that we have designed in the case of solid state sensor, and that we can denote it in the form of p of t that is equal to the function of beta b into theta of t, and here f of b, that is a function of characteristics of the semiconductor. We can denote that, and what kind of material normally we are using for that, and based on the material property that may change. And theta is the position of the semiconductor at the time t. And obviously, from this diagram, the exciter wheel will change continuously, and that's also influencing to change the current that carrying through the semiconductor, and that will influence to change the magnetic flux inside this system. And the output signal is a function of the characteristics of the semiconductor as well as the position of teeth. That's all. And moving to the next slide. And obviously, we can say here the Vmax, the maximum output voltage should be the maximum of function of magnetic flux, and that is denoted in the case of Vmax. And the minimum voltage will give you from the condition of f of b minimum. That means minimum magnetic flux density when influence to change or influence to occur the device for the minimum voltage at the output. Okay, and obviously we can say here, and these all are the main parameters, and these all are the main consideration that we need to go for the design requirements of these kinds of solid state sensors. And this next parameter that we need to consider as sensitivity, and how your system is function in the case of sensitivity, and how sensitive your device, and if your device is capable of sense the little change in the output of physical quantity, that is known as the sensitivity of the device. And if your device is capable of detect the smallest change at the input as the output, that becomes known as the sensitivity. And the ability of the system is gives you the smallest change at the output, that is sensitivity. And S is we can here denoted as S is equal to the magnetic flux density maximum minus magnetic flux density minimum divided by the mean value of the magnetic flux. And B mean, obviously we can say here B max plus B minimum divided by 2. Okay, and in this section we have discussed about what is solid state sensor and what is the structure of solid state sensor, and what all are the parameters influencing to change the Lorentz force F, and how the signal should be, and that means that should be in the form of electrical signal, that is denoted in the case in the form of V of t. And next one, the sensitivity, what is sensitivity and how we can express solid state sensor sensitivity in sense of a magnetic flux density. Okay, and next topic is magnetic speed sensor requirements, and what are the requirements we need to design a magnetic speed sensor. And typical variable reluctance sensor requirements of automobile application is listed over here. And first one, sensor signal, it is usually defined as the peak to peak value, and how your output signal would be, and is it in the form of current, is it in the form of voltage. That is the first requirement when we are going for the design. What kind of signal we require, it is in the form of change in current, is it in the form of change in voltage. Okay, that is the sensor signal parameter we need to consider for the first as a first requirement of for the design. And the geometry of the design, and how your system and where your system is going to embedded with that a perfect system or another system, and how your system should behave in a space. Okay, so geometry of the system is one of the consideration. and the speed range, and what should be the speed range of the device that should sensitive. Okay, and if your exciter wheel is rotating at 10,000 rpm, and is it possible for your device to get the output if this exciter wheel is rotating at that high rpm. Okay, and speed range, and that's also one of the parameter, and that kind of design you require if you're going for the higher speed, and the temperature rate. And is your designed system is capable of give you the perfect output at high temperature or low temperature, and how your system is influencing on the change in the temperature. What is the and that this is a temperature requirement, and acceptable noise level. And obviously we can say that all system is influenced with different kinds of noise when they are functioning in normal real time, and how your system is capable of noise in immunity, and how the capability of the system is reject the noise, and what are the acceptable noise level in your system. Okay, and here we can say here one point, and your speed sensor gives you a small change in the output, or the output should be in the form of microvolt range, and we can say here that is very less when we are going for the consideration. And if the voltage is changing in microvolt range, and if your system is affected with external noise, and that maybe gives you some faulty result. Okay, is your system is capable of gives you a high stable output even though it is in a noisy environment. That should also we need to consider here. Okay, these all are the main requirements of magnetic speed sensors. Okay, and these are the some consideration when we are going for the automotive applications, and this is just an example, and signal peak to peak voltage, and how what should be it will be, and at 25 degrees celsius, and what may be the change at 150 degrees celsius, what may be the change, and geometry, how we can go for the geometry, and in case of inserted magnet sensor as well as friend magnet sensor, and multi magnetic sensor. Okay, and for the different kinds of application in automobiles. Okay, and what should be the noise signal ranges for the consideration, and if your system in temperature consideration when you're going for, and the system is capable of functioning from minus 40 degrees celsius to 150 degrees celsius plus, and some multi magnet sensor will survive within the temperature range of minus 40 to plus 200 degrees celsius, and this is the temperature consideration or the requirement aspect in the design in the design aspect. Okay, and moving to the next slide, VR sensor noise, and what is noise then? Okay, and what are the consideration we required when we are going for the perfect design for avoiding this kind of noise? And this the diagram will gives you a normal output, and this is not influenced with noise, and this output is not influenced with noise, and this kind of signal we are expecting, but unfortunately we are getting this kind of signal at the output. Okay, and this is not possible if you're going for the perfect design. We should eliminate this kind of noise, and what are all the consideration we required for eliminate this kind of noise. Okay, and here the noise should be measured. The worst condition, it may be occur. The noise may be occur. That means expected design or expected output like this, and due to the high temperature or highest engine rotation, or maybe the sensor position, or maybe the flex linkages, or maybe the external interferences, the output of the system gives you these kinds of output from the deviation of expected signal like this. Okay, and this may lead to you some faulty result, and we need to go for some consider parameters for reducing this noise. and what are the consideration. Let's talk about that. Okay, and before that, let's talk about the signal, the output signal. What should be the output signal? What are the parameters depending on the output signal? As we have discussed in the case of solid state sensors, and this is a speed sensor we are going to discuss about here. And V of Vs is equal to Vs is nothing but the induced signal sensor and induced signal and the sensor coil, and n d phi divided by d theta divided by dt. And so d phi n is the number of turns of the coil and inside of your system sensor system, and theta is the angular position, and t is the time. Okay, while rotating it, we can say that some kind of angle is occurring, and some kind of angle we can consider here, that is nothing but the theta, and t is a time of the rotation or time of the movement. And here the omega we can represent d, the derivative of v with respect to t, and that is nothing but the omega. When we are substituting it, we will get d phi divided by dA, and a similar equation that describe the noise signal as a function of relative sensor wheel position. Okay, and the relative the noise influenced parameters we can represent in the form of dA, and then the V is the signal output should be, we can say that minus of n d phi divided by dA into dA divided by dt. And this is the theory of the mathematical model of noise analysis. And going to the representation, three-dimensional representation we required. In sense A is nothing but in sense of x, y, z we need to consider. Okay, three-dimensionally we are considering the change in the sensor voltage with respect to noise. Okay, and I mean to say here, and we're getting some a signal, but that signal is influenced with some noise parameter, and that parameter can represent in the form of A here. Okay, just we have described about some equation related to the noise and the relation with the noise and the output signal. We're focusing there. And the solution for the noise problem is, and if you are increasing the size of the wire, then the signal or noise, the signal to noise ratio, it will reduce. And if you're going for the wire size, if you're increasing the wire size here, or decreasing the wire size, and it will decrease the noise. And if you're increasing the air gap, automatically the noise as well as the noise to signal ratio is reducing. Okay, and from the diagram it is reflecting. And the air gap also, we have already discussed that the noise signal is also reducing, and if you're going for the higher air gap, and signal is also reducing, that I mean to say here, noise to signal ratio is reducing when we are going for the air gap if you are going to increase. Okay, and this is how we can rectify the noise affected in your system for the magnetic sensor DC. Okay, and that's all about this module. And in this section, we have discussed some details of just solid state sensor and what are the solid state sensor and how does it work, and some equation related to the solid state sensor, and one diagram, and the output signal representations and influencing of output signals, and about magnetic field sensor requirements, and five requirements we have discussed here about VR sensor noise. Okay, variable reluctance sensor noise. What is noise then, and also how we can reduce the noise. Okay, when we are going into the deep of the design of this kind of VR sensors. Okay, and that's all. That's all about this module. Thank you.